Okay, it's just after 2 p.m. Eastern Daylight Time, so I'll get started there now. My name is Andrew Grannell. I'm a statistician here at Statistical Solutions. I'm here with my colleague Eoghan Murphy, who's also a statistician here. Welcome to the second webinar in our SOLAS for Missing Data Analysis webinar series. As you remember, you may have remembered that our first webinar was back in January on the predictive model-based imputation method. Today's webinar is going to be on the Mahalanobis distance imputation method. So let's just get started then. So just the outline for today's webinar. It's 30 minutes long. I'll just do a quick summary and recap of the last webinar where we defined what the concepts of missingness, missing data patterns, and just a brief summary of the last model, predictive model-based method. I'll then run through the methodology behind the Mahalanobis distance matching method. I'll run through a short worked example and give a little example of post-imputation analysis in SOLAS, and we'll have time for questions and comments throughout the webinar. Now, I'd just like to say the format of this webinar is quite informal, so if you want to ask a question, due to the volume of people here, everybody is muted, so if you'd just like to put a question through the text box that's provided, Eoghan here will be getting back to you as quick as he can, and I'll be answering a few as well as the webinar progresses. Also, if the webinar screen is too small, there's a zoom option there on either the top left-hand corner or the bottom right-hand corner, depending on which version you have. So if you need to enlarge or reduce the size of the webinar screen, just click on the little arrow beside the number and you can zoom in and out to your preference. So also just let me know at any time if you can't hear me or understand me. Just put a little comment through the text box to Eoghan, and he'll let me know, and I can go through anything and go back over anything. Okay, so just a quick recap then of the last webinar. So we define missing, the different types of missingness. There's missing at random, and this is where the missing data does not depend on the observed data. And then there's a specific case of that where there's missing completely at random, where the missing data does not depend on the observed or the unobserved data. And then there's missing not at random, where the missing data depends on the unobserved data itself. Looking at the different missing data patterns, monotone and non-monotone. A monotone pattern occurs when the variables can be ordered from left to right, such that a variable to the left is at least observed as all variables to the right. For example, if variable A is fully observed and variable B is sometimes missing, A and B should form a monotone pattern. Monotone patterns always kind of occur in close approximation and can be quite common. They normally tend to appear in longitudinal studies, which makes sense. And then finally, from the last webinar, we talked about the predictive model-based method, where it incorporates an ordinary least squares regression model for continuous and ordinal variables, and it employs discriminant analysis and imputation for the categorical and nominal variables. As you did a link here at the bottom of the screen, if you can see it, this is where you'll find a recording of the previous webinar if you want to catch that. It's at www.solasmissingdata.com/resources/webinars on demand. So moving forward with today's webinar then, the Mahalanobis distance matching imputation methodology, I'll just run through quick few definitions and equations, how SOLAS does it, and then I'll run through an example. So what is the Mahalanobis distance and how is it incorporated into multiple imputation? Well, the Mahalanobis distance, defined back in 1936 by Mahalanobis himself, is defined as this equation here, dm of xiy due to the square root of xiy transpose S inverse times xiy, where xi is a vector of the ith fully observed case, and y is a vector of covariance for the case with missing values. So in SOLAS, when you're using this for imputation, sorry, I'll just say as well that S is the covariance matrix, and the second equation here is an example of a two-group case, and this is I'll show you an example of this in a minute, where S1 and S2 are the covariance for group 1 and group 2, and N1 and N2 is the sample size for group 1 and group 2. So in SOLAS here, what you do is you define certain characteristics which would be determined appropriate by the researcher in the circumstance. You'd use these characteristics to match different cases. So if you had a missing response from one case, you'd use other variables to match with a case that had the same data point observed, and we take multiple groups of these cases and select from them randomly to impute. So this brings us on to defining the donor pools. So using the Mahalanobis distance method, there are two ways of defining the donor pools, and the donor pools are the important bit, because the donor pools are the pool of values that you randomly select from to create your multiple imputations. So you calculate the Mahalanobis distance from your missing person or case, and you calculate that to every other case in the data set. And based on those characteristical variables that you have already defined, you will select then. You can select either a subset of the C closest cases, where C is just a constant, the C closest cases, and you can select randomly from that pool, where SOLAS uses a default of the top 10 closest cases, or you can use a subset of the top D% closest cases, where you specify the percentage of closest cases in the data to form the donor pool, where SOLAS uses 10% as the default. So again, guys, if you have any questions, just fire them in, and we'll be dealing with them as they come in. Eoghan will be taking them, and I'll be answering a few there as we go through too. If you want me to go back over anything, just let me know. And again, if you have trouble hearing me or understanding me, please let us know, and we'll go back through things. Okay, so so moving forward then, next we're just going to run through a worked example. This is where I'm going to take a data set, and I'm just going to do some quick pre and post analysis and do some kind of comparisons and give you a bit of an example of how you could do quick analysis in SOLAS. We also have a leprechaun creeping in here because we're coming up on Patrick's Day here in Ireland, so I thought I'd just include that there for you. So I'll open up SOLAS there now, and we'll go through the worked example. So again, if the webinar window is too small, just zoom in there using the feature at the bottom of the screen. So this is what you're presented with when you open up SOLAS. You can open up a new data set or an existing one. Currently, the file formats that exist in SOLAS are .csv, .text, and .dat files, and also Excel file format is read into SOLAS. And something that is coming soon is SAS transport files we're going to include too, so that you can import SAS files and export just SAS for further analysis. So we also have a script language window here where I can just show you where you can input the SOLAS language to create your own imputation model, and then it'll run an output in the log and show you the output. Or you can run a model in SOLAS, and you can generate the code and you can alter it to whatever way you wish. And also the help documents are all here too. So I'm going to open up an existing database to show you. So here we have a treatment miss, it's called, and what we have is 9 variables and 188 patients. And essentially what we're doing is we're just going to be comparing a treatment, and we have 3 characteristics, age, height, and weight, that were measured at the time of the treatment. We also have a variable indicating whether the patient was treated or not, yes or no. We have their cholesterol level and their dosage 1, 2, and 3 for the 3 different drugs that they were dosed with, whether they were treated or not. So first, when you open up a brand new data set, you may like to see the impact of the missing data in the data set. So here in SOLAS, it's just view, and you can see the missing data pattern and see to the extent of how the missing data is there. In SOLAS, you can just click and drop. That's the kind of function that is in SOLAS, click and drop, or in this case, if you just want to see all the variables, you can just hit use all. So now a new window will pop up with the actual missing data pattern, and it's a grid here which shows you the missing and the present data points, where the white cells represent the present or observed data points and the blue cells represent the missing data points. Now, I'm sure all of you are quite familiar with working with large data sets where it would be timely to scroll down, as I'm doing here, through a lot of rows. So we also added this view and collapse function, so you can collapse that table into a summarized table. So once I've collapsed it down now, essentially what I've done is just collapse the number of rows. So the rows now are telling me that 141 cases out of the 188 are completely observed. We have one variable, or one case, one patient that has these 2 missing data points, 2 with this particular missing data point, 42 cases with this particular missing data point, and so on. We can also, as I was saying explaining earlier, we can also break this down into the monotone, non-monotone pattern by going hitting view and monotone pattern. So now the red represents the monotone missing data points, and the green represents the non-monotone missing data points. So this is the extent to which our database, our data set here has missing data. And we can do a bit more further exploration if we want to do some more exploratory analysis into the relationship and how the missing data is affecting the relationship between 2 variables. We have various plotting features. You can do scatter plots, histograms, box plots, etc. But we have this margin plot as well, where you can essentially plot a scatter plot, but there's extra information given within the margins or within the axes that give us further insight into the missing data. So I'm just going to show you a quick example of this. I'm going to plot cholesterol versus dose 1, where cholesterol, I didn't mention there, but cholesterol has the most missing data points in the data set here. And again, we have this grouping variable. You can split it up. I'll do that in a second. So here we have the scatter plot. It's where the blue dots here represent the observed variables for both dose and cholesterol. So this point here is the value for dose corresponding to this value for cholesterol. But in the margins, or down in the axes here, on the x-axis and on the y-axis, we have box plots. The blue box plot here denotes or defines the distribution of the observed data, and the red box plot shows the distribution of the red data, or the missing data, sorry. These red dots give you the actual data points where the missing data is occurring. So this red dot represents we have the value for dose 1, but we don't have the corresponding value for cholesterol. And this red dot here says we have the value for cholesterol, but we don't have the corresponding value for dose 1. And it gives you you can find some quick insight into your data by doing these kind of plots to show the distribution, because you can see here the distribution of missing data for cholesterol and dose is quite small, but it's quite varied for dose 1. Also, you can see some outliers in the data too. So so that's, I can also shall I do it? So I can replot this by grouping. So I'm going to group it into the 2 groups: have you been treated or not treated? So just use a grouping variable, click OK, and now there's 2 different colors, orange and blue. One is for have been treated, and the other is hasn't been treated. And again, I can actually split that into 2 different plots if I like as well. So now one plot is for no, and one plot is for yes, I have been treated. And as you can see here, there's no missing data for cholesterol in the yes treated, and there is missing data for cholesterol not treated. So again, just some nice comparative, graphical comparisons, just to get some good insight into your data before you do any analysis. Also, there's a nice feature here in SOLAS that you can actually just define all your variable attributes. So you can set what type of a variable it is. So in the example of the treatment variable, Tx, it's a categorical variable, so it's got two groups. So we set it as nominal, you can show the group names, you can define the category names, etc. So it's quite a handy feature. So just to do some analysis before I do any imputation, and it's going to make sense after, because I'll do the same analysis again after I do imputation. So just to do I'm going to do a quick t-test just to compare between, I'm going to compare cholesterol levels, the two-group t-test. I'm going to compare cholesterol levels between the treatment groups, yes and no. And I'm going to say our null hypothesis is that the means are equal. And also, I don't have to do any normality checks here because SOLAS does that. SOLAS will say if it fits the assumptions for a t-test, it'll run a t-test. If it doesn't fit that, it'll run a non-parametric test instead. So I'll click OK. In the output, then we're given a table for the mean, standard deviation, and sample size for each group and overall. So there's 73 cases in each group, yes and no. The mean cholesterol level for the no group is 222, and the mean cholesterol level for the yes group is 243. And our p-value here for the test is less than 0.05. So we're saying there is a significant difference between the two groups. We can also run some comparative plots. We can run a box plot here just to see the difference between the two groups. We can also run a means comparison, so you can see here there's quite a difference between the two means. And we can run a histogram again, just a quick graphical checks on your test there. So now I'm going to run the imputations. So again, just go analyze multiple imputation. Today we're going to do the Mahalanobis distance matching method. So as I said before when I was explaining, the fixed covariates you need to define are the characteristics that you want to match groups with. So you're going to calculate the Mahalanobis from your missing case based on these characteristics. So I'm going to put in age, height, and weight. So I'm going to compare people on similar age, similar height, and similar weight. And I'm going to impute on the 4 missing data variables. Now an interesting question has just came in that one person asked that does the variable have to be completely observed to use as a fixed covariate? I'll just give you an example. If I try and drop an incomplete variable into the fixed covariates, I get a message saying this is an incompletely observed covariate. So what it does is it gives you 3 options. You can use hot take imputation to fill in the missing values and use it as a covariate. You can use a dummy variable or an indicator variable to indicate the missingness. Or you can just run the imputation but exclude any cases that are missing from that covariate or that variable that you used. So I'm not going to do that today, but that's the options. I'm going to run 10 imputations. The minimum is 2 and the maximum is 50 in SOLAS for running imputed data sets. You can also define a grouping and center variable. You can also add more information about the non-monotone and monotone missing values. And here is, as I said, there's two ways you can do defining the donor pools in SOLAS. So you can use the top 10 closest cases and randomly select from that 10, but you can increase that or decrease it wherever you feel, or you can use the top 10% closest cases to define the donor pool that you randomly select from. You can also define refinement variables for each imputation. So I'm just going to run this imputation now. So it's going to generate 10 data sets for me. So now we're given, this is the output from the imputation. We're given the exact same, except now the missing data has been filled in with red and green values. The red values signify the monotone missing values that have been imputed, and the green values represent the non-monotone values that have been imputed. And also, if you look down the bottom here, we have tabs now, 10 tabs, one for each data set. So you can look at all the imputed data sets, and you can look at the different values that have been given. And you can also perform analysis on each individual one or all of them together. So this can, at this phase now, you can also save this as an Excel file where each data set will be a different spreadsheet in Excel file format. And what will be coming soon is that we will have SAS export files that you can export these 10 data sets into SAS. So I'm going to do the exact same analysis as I did before, the t-test between the two groups. So we're going to use the treatment variable as the grouping variable, and we're going to compare cholesterol, and we're going to say that the mean difference is 0. Click OK. So now we have the exact same windows popped up, except this time at the very bottom you can see there's 10 tabs, one for each data set. Also, the results have slightly changed now. So the p-value was 0.02 for the original data set, which was less than 0.05, and now for this data, for this imputed data set, it has crept just above the 0.05 threshold, the 5% level of significance, and now it's 0.07. So now it's slightly not significant. So now it's telling us that there is no difference between the two groups. Again, if you look at other data sets, this is slightly above the 0.05 threshold. Again, this is quite substantially above, and this all depends on the values imputed. Again, this one is above the 0.05, above, and above. So the data sets have come in slightly up. So now it's slightly changed. So this leads us to believe that, you know, or whether just to investigate, like, has our original data set been slightly biased or skewed in one direction due to the missing data? And this raises the question that by imputing multiple times, are we getting a better picture for what the actual population in the study should be like? No, we're not saying this is just the answer. We would feel now that you should go on, if it changes your results, you should go on and do some further sensitivity analysis and further investigation. And you can also do some further stress tests, like using different models and running the same tests, comparing the results to see how volatile it is to changing the model, etc. So so that's pretty much what I wanted to go through with you guys today in this Mahalanobis distance matching imputation method, and also what I wanted to show you in SOLAS. So I think if there's any questions at this stage, we'd love to take any questions or any comments right now. If you'd like to visit the website, it's SOLAS.wmv. If you'd like to contact us, if you have any questions after that come to you later, you can contact us at support@statsol.ie. We also have a discussion forum at solasmissingdata.com/forum. We'll be posting a recording of this webinar on our website, so you can come back and view it again. And if you have any questions again at any time, you can email us at that email address. And we will also be sending out one of our own white papers on Mahalanobis missing data, or Mahalanobis multiple imputation method, with the full description of the model or the method, and supporting documentation. So I hope you've all found it very informative and you've enjoyed it. I'd also like to wish you a happy St. Patrick's Day. It's coming up on Saturday. We're all going to have a great time here in Ireland, and I hope you guys do too. So so I'll just take a break now just to look at any questions or comments. So we'd appreciate any comments or questions you have from you. Thanks. Okay, there's been a few questions flying in there, and Eoghan's been getting back to you pretty quick, I hope. There's a question came in of how do you define what is the closest values or the closeness. So essentially, what it is when you you select your characteristic variable. I'm just going to say, for example, age. So you're going to take people with similar ages, and the person with, say, one person has a missing data point and is aged 27 years old. You're then going to select out the other 27-year-olds and people around that age, and you're going to calculate the distance, the Mahalanobis distance to all those people, and the ones with the shortest Mahalanobis distance metric, you're going to take those guys and take, depending on how you've defined your donor pool, you're going to take, for example, the top 10 closest Mahalanobis distance people, and you're going to put them into a pool and randomly select from that pool to create your multiple data sets. And then you can run your run your post-imputation analysis based on that. That's a very crude and simple, simplex description of it. And again, there's a lot more information contained in the white paper that we'll be sending out after this webinar on how the actual calculations are run. So I think that's it for the webinar today. We'll be following up with all the other questions that you may have after the webinar. Just again, email us at support@statsol.ie, and we'll be happy to follow up on you. And we'll just sending a follow-up email with the link to the recording of the webinar and white paper. So again, I hope you've all enjoyed the webinar and that it's been informative to you. And happy St. Patrick's Day.